In the next subsection, we'll see how the range minimum query problem, the first of these abbreviations, connects to some of the others that you might hopefully remember from Unit 8. We'll come back to those. And then that might give you more motivation for studying this more abstract problem. The range min query problem is just on these arrays of numbers. And you might ask, why would you want to know the minimum in a certain range? What's that good for? So remember from Unit 8, there were a few things that we did where the other abbreviations from the section title popped up in. The first thing was we were looking at suffix trees, these beasts. Just so that you remember, it's the compact trie of all suffixes of a text, right? And we were using these for different string algorithms or making different string problems fast. One of those was the longest common extensions problem, where we this was part of solving more interesting questions with suffix trees. We used this as a building block, and then longest common extensions could be reduced to finding lowest common ancestors in the suffix tree. We wrote that at the time like this. So if I want to know the longest common extension of two suffixes that start at position I and j, then I can look in the suffix tree for the two leaves that correspond to those two suffixes and find the earliest where their paths join if I move up, or the lowest common ancestor if I move down from the root. And the string depth of that node, that was our longest common extension, or the longest common prefix. And well, we've had this example of the leaves 5 and 7, but I think it's too small. So if you want to see the example again, maybe we go back to Unit 8 instead. So that's the connection between those three things. We had longest common extensions of two positions. How far can you read to the right in the text and see the same characters from I and j, which is the same as the longest common prefix of two suffixes. And we connected that to the lowest common ancestor of leaves in the suffix tree. The second bit that is borrowed from Unit 8 was this promise that we can do lowest common ancestors, LCA queries in trees, in an efficient way, namely in our notation, theta n pre-processing time and order 1 query time, constant time for a query. Okay, so that was the promise back then, but I didn't tell you how to do it. Then there's one last thing that we studied back then. And that was along the journey of getting rid of the suffix tree for our problems. Instead, we used the suffix array. Then we found the suffix array is not good enough for some problems. We also need this LCP array, the longest common prefix array. And the longest common prefix array stores this longest common extension for two adjacent leaves. Right, remember we had this picture that we walk along the leaves of the suffix tree from left to right. Now, whenever there's a green connection between two leaves, they are adjacent in the order of the suffix tree. And then we have, or in alphabetic order. And for those two, we have the lowest common ancestor, we have the longest common prefix. So the string depth of lowest common ancestor was 0 here. Between these two, it's string depth 1. Between these two, it's string depth 2, and so on. So the LCP array, as we defined it in Unit 8, already has some answers for LCE queries, but only if these two leaves are adjacent. So I could, for example, ask for LCE of 5 and 7 directly by finding the right LCP entry. But if I'm asking for two other leaves that are further apart, there's no entry in the LCP array that directly gives that answer. But you can translate between the two. And for that, let me zoom into this picture a bit. And let's find, again, 5 and 7. These are adjacent in sorted order. The suffixes aban and an, there's nothing in between. There's no suffix that's between the two in lexicographic order. That's why the LCP array has directly an entry that tells you the longest common prefix between those two. Same as what I've just said. But what if you ask this about an arbitrary collection of two, an arbitrary selection of two suffixes? For example, I could ask about 5 and 1. So these are two suffixes. They're not adjacent. So what's their longest common prefix? They span a certain range in the alphabetic order, and they span a certain range in the LCP array as well. And the thing is that we have to find the smallest entry in that range to get their overall longest common prefix. And the reason for that is if you look at the strings, these red strings, the things that they share, that adjacent suffixes share, kind of the lowest common denominator is what determines the longest common prefix between this one and this one. So all of those start with an A, which means from here to here, I have to have at least one thing that they share. From here to here, I have 2, which is more than 1. From here, we have even 3. But the smallest number will always dominate, because that means you have the same minimum number all the way through. That's the longest common prefix between those two. If there was a longer common prefix, then it should be shared among all those in between. That's by alphabetic order. If these two shared 2 letters, so the first 2 letters here were the same, then anything in between in sorted order also has to start with the same 2 letters. So we find that the longest common extension of 5 and 1 is the same as this range minimum query in the LCP array from, well, the positions here are numbered a bit awkwardly, remember, 1, 2, 3, 4, 5, and so on. So from position 2 to 4. And that connection is general. So if you want to express this in the general case, what you get if you have two starting indices of the suffixes, the starting index is not the position in this list, that's the number in here. So the first step, that's why that slide is here, is to translate from starting index to the position in the sorted list. That's the rank array. So we take I and j and convert them to their ranks on the right-hand side. We do that with both. Now these numbers, they might not be in sorted order. It might be that they swap relative positions by moving to the right. That's why we have to take the minimum here and the maximum here. And the +1 comes from this convention of the LCP array to sit between two suffixes, but then it starts with index 1. But overall, the connection is relatively direct. If you want the longest common extension of two suffixes, you need to find the range minimum query of some part in the LCP array. All right, so again, the connection is just translating the pictures from one side to the other. But if you have things in sorted order and they share a certain common prefix, then anything in between has to share at least that much. And also, if there was anything longer, then they would also share this. So it's an exact equality. So if we translate what that means for any solution for the range min query problem to longest common extensions, it means that we get essentially the same running time. If we have a PQ solution for range minimum queries, we can use that solution using the inverse suffix array to directly answer longest common extension queries. And we use the same pre-processing time plus I guess there should be a plus order n, because we need the time to compute the suffix array and the inverse suffix array. But the query time stays the same. And any interesting pre-processing time will also be at least linear. I think the cleaner way to express the same thing here is for longest common extensions, when we're already given the rank array and the LCP array. Yep. LCP. So if you remember what we wanted, the claim here was we can do it with linear preprocessing and constant query time. That would be the final goal for the range minimum query problem. And you can compare that to what your guess was, what might be possible.